Okay, so I'm going to talk a little bit about the binomial distribution, why we use it, then how to use the StatCrunch to do the binomial and Poisson. And that they're both discrete probability distributions, and they're closely related, but they are different. So binomial means bi is there's two outcomes, two things can happen: yes, no, right, wrong, fail, not fail, broken, not broken. Just two things that, there's only two choices. Now, aside from that, could be like a multiple choice test where you have a correct answer and a bunch of wrong, but that would still be the probability of a right against probability of a wrong. So they're generally going to say a success is what you're looking for. And P, like I have my little formula here, will be the probability of a success. So I have this written. This is kind of old school. In the last 10 years or so, this notation has kind of gone away. And this is where we would have NCK. My other notes I'm going to post will probably have NCR, but the idea remains the same. This is standing for a combination. And I'm going to skip right over these formulas and go right to this example. Suppose you toss a coin 4 times, and I'm going to say the probability of a head is 0.2. So it's a loaded coin. Okay, it's not fair at all. Probability head's 0.2. That means probability of a tail has to be 0.8. Because those two have to add up to 1, because those are only two outcomes. Again, two outcomes. And here I've written out this sample space. Now what I want you to think about here is there's 4 different trials happening here. In each trial there's 2 outcomes. So 2 times 2 times 2 times 2 gives me 16. So there's 16 different outcomes. And I listed them all out. But it's kind of a pain if this becomes 5 trials, that's 32. 6 trials, 64, and you're not going to be able to write them all out. Okay? So where the binomial helps me is if I want to find the probability, in this case, of 1 head. So I have it written out here, all the outcomes that are just 1 head. But if there's 1 head, that means there's 3 tails. And what I want you to concentrate on, this x equals 1 is the number of successes we're looking for, in this case, heads. If there's 1 head, there's 3 tails. So this equates to everywhere I have a t, I'm putting a 0.8, and everywhere an h, I'm putting a 0.2, because each trial is independent. And if I were to multiply these out, okay, all these 3.8s and a 0.2, every one of these would be the same value that I'm adding up. And I could care less what those values are. But I just want you to see that there's always 3.8s and 1.2. Well, how many different ones times does this happen? Well, it's 4. And that's coming from 4C1. And if you do 4C1, you have 4 flips. You're looking for 1 head. 4C1 is going to give you 4. Okay, you punch in your calculator, believe me, whatever, do the formula. But that 4 is telling me there's going to be 4 different arrangements of the 0.2 times 0.8 to 0.8 cubed. So instead of writing that all out, this binomial, here's the formula here, this is the 4, that's where the 4 is coming from. The p is 0.2. The k is how many am I looking for? I'm looking for 1 outcome. So that's why that's a 1. 1 minus 0.2 gives me 0.8. And it's a 3 because I did 4 trials. And these exponents always have to add up to the number of trials. So the probability that I flip this coin, it's not fair, but if I flip it 4 times and I get 1 head, is about 41%. Find the probability of 2 heads. Well, scroll this up a little bit. X equals 2, so I have 2 H's, 2 T's, and I wrote down all the different combinations here. Now, we can, if I have the sample space, what I'm trying to get at is we can eliminate this entire step of writing out all these outcomes if I just believe in the formula. This is saying I have 4C2 because I'm looking for 2 heads, and 4C2 is going to be 6. 4 choose 2 is 6. There's 6 different ways that can happen. And I'm going to get 0.2 squared because I want 2 heads, 0.8 squared because I want 2 tails. And that gives me 15, or 0.1536 as proportion. So in here they're just written out. I did it via formula to get the coefficients here. It's 4C1, 4C2. It all means the same thing. Now, it's important to me that you understand why it's a binomial. It's a binomial because there's 2 outcomes. There's a fixed number of trials, in this case 4, and you have the probability of a success, which also means you have the probability of a failure, because the 2 have to add up to 1. And it's great if you want to work it out by formula. That's lovely. I just want you to think about something here. Instead of 4, if I do 10 flips, that's 2 to the 10th power. And that's going to be a very large number. Okay? The other thing I want you to think about is if you're going to write out these formulas, this is for x equals 1 or x equals 2. If I do something where I want the probability of at least 1 head, or a probability of 1, 2, 3, 4, 5, or 6, or a probability of 1 to 10 heads, you would have to have one of these formulas for every one of those outcomes. If it's 1 success, 2 success, 3 success, whatever. Now, if you want to write them all out and do them by hand, you are welcome, but I would prefer that we use StatCrunch. And assuming we can get into StatCrunch, the main button that we use here is Stat, and you would go to Calculator. And in this case, we'd go to Binomial, because that's what we're talking about. You'll use one of these throughout the semester. But we'll go to Binomial. I'll bring this up. And is the number of trials. So let's say we're flipping a coin 10 times. Let's say probability of getting ahead is 0.2. And then down here is asking different questions. Probability, this is how many successes I'm looking for. This do equal to 3 heads. And if I get equal on there, it'd be nice. Equal to 3 heads. So I want to flip the coin 10 times. Probability of a success is 0.2. What's the probability that in this situation I flip 10 times and get exactly 3 heads? Keyword exactly, so just equal to 3. That'd be 0.2013 or around 20%. That quick. If I asked the question, if I wanted at least 3 heads, or excuse me, at most 3 heads, so it would be 0, 1, 2, or 3, at most 3 heads. So think about that. 0, 1, 2, 3. You would have to do that formula 4 times and add it all up. Or put it in and there you are. So there's a difference between, I think sometimes people get fixated on, I got to use the formula to understand what's happening. That doesn't mean you understand what's going on. What's important to me is, do you know that this is a binomial? Do you know it's a binomial situation? That's what's important. Because, yeah, some of us are going to be faster at a calculator. I guess my point is, if you're using the calculator, what's really the difference between that and software? But that's something you have to think about. Now, on to the Poisson. And I don't have, I'm not going to open notes for the Poisson. Poisson is a different situation. I'm just going to bring this up. Again, I went to Stat, Calculator, Poisson. And you'll see this is dependent only upon the mean. So the mean is something like the average amount of defects on a sheet of marble, or the average number of phone calls to a call center in 1 hour. It's like a rate. Okay, the number of people who are in car accidents in a day, number of people who come down with some disease in a week. You can relate that all to a mean. And this Poisson is completely dependent on the mean. There is not a fixed number of trials with the Poisson. And that's kind of important to realize. There's not a fixed number of trials. You could have an infinite number. Okay? So a situation would be, we have a call center. And I say the number of calls into the call center in any given hour. And we're going to go on either times or sheets or whatever units we're talking about are independent of each other. So I'm going to say, when this call center is open, the number of calls into that call center per hour is around 56. That's the mean. That's what they average. So what's the probability that I see exactly 62 calls? Okay, so exactly 62. It's not very likely that I'm going to see exactly 62 calls. If I change the question, what's the probability that I see at most 62 calls? So that means 0 calls, 1 call, 2 calls, all the way up to 62. And I want you to think about that when you look in your book and you look in the notes I post on well, assuming I do post it on the Poisson, you're going to see there's going to be 63 formulas you'd have to add up to get this. And again, yeah, you could do it. What I'm caring about is, do you know what's Poisson? Do you know the difference between a Poisson and binomial? And can you get the number? This actually is the least important part of the process to me. When we're on a test and I give you a situation, I'm not going to say use binomial, use Poisson, you have to figure it out. You choose the Poisson. If it's a 5-point problem, you have 4 of the points. If you get the right answer, that's 1 extra point. Okay? So again, you have to have a mean, and then they're going to ask you questions for exactly or less than. I could go greater than. Probability of at least 62. So I could say 62 or more calls. That's around 23%. Or I could do something like this, between. And this also works on the binomial. This say I average 56 calls. What's the probability I get between 50 and 60 calls? Well, around 54%. So then you can start making decisions of, well, how many operators do I need at this call center? What's my, do I have enough capacity to handle that many calls? Situation like that. But again, mean difference. Poisson has a mean. There's independent trials, and the trials are time units or areas or volumes or days or things of that nature, items. Binomial has 2 outcomes, a fixed number of trials, and they're independent. So I'm going to put a sheet up in the content area that's going to talk about using StatCrunch, and it's all written out in words with examples. But I would like you to watch this video and try StatCrunch for me. All right, thank you.